we're going to use our previous 4 items from definitions of limits to come up with some more properties of limits. The first one is we want to know what the limit of x approaches a of a constant times the function is equal to. Well, I know this is a product, k times f of x, so I'm going to use my limit of a product formula, and that gives me that it is the limit as x approaches a of my constant times the limit as x approaches a of f of x. We already know that the limit as x approaches a of a constant is just that constant. And the limit as x approaches a of f of x is the limit as x approaches a of f of x. This is called the constant multiple rule. It says if I have a constant times a function, the limit as x approaches a is the constant times the limit as x approaches a of that function. The next one, I have f of x minus g of x that I'm taking the limit as x approaches a. Well, this is very similar to my sum formula, but I can rearrange this using prior properties to actually come up with what the answer is going to be. This is the same thing as the limit as x approaches a of f of x plus -1 times g of x. All I did there is I factored out the -1 so I could write a plus sign because I do know what the limit of a sum is. Well, this is going to be the limit as x approaches a of f of x plus -1, let's write it properly, plus the limit as x approaches a of -1 times g of x. Here I have a constant times a limit, so I can pull that constant out in front. And if I pull that constant out in front, I'm going to get a negative sign there. So the final form of this is it's the limit as x approaches a of f of x minus the limit as x approaches a of g of x. And the final one that we're going to cover in this video is the limit as x approaches a of f of x raised to a power. Well, raising something to a power means multiplying it by itself over and over and over again, which brings us back to the limit of a product thing. So I'm going to write this as the limit as x approaches a of f of x times the limit as x approaches a of f of x. And I'm going to keep on repeating that n times. Well, if you realize that, hey, this is going to be a number, times the same number, times the same number, times the same number, well, in essence, that number that I'm multiplying over and over again is the limit as x approaches a of f of x. And because I'm repeatedly multiplying it, I can just raise whatever that number is to the appropriate power. So what it says is the limit of a function raised to a power, well, a function raised to a power that I take the limit of is the same thing as the limit of that function raised to a power. Using all of these properties, we're going to be able to show that it's going to be very easy for us to take limits of polynomial functions. One mathematical operation that I did not put up here is the limit of a quotient. For example, the limit as x approaches a of f of x over g of x. Well, the actual answer to that is the limit as x approaches a of f of x divided by the limit as x approaches a of g of x, provided that the limit as x approaches a of g of x exists. If the limit does not exist, I would get a function that has a fraction dividing by 0, and we cannot have that. The other thing is that the limit cannot be 0. So two things: the limit of x approaches a of g of x exists, and the limit as x approaches a of g of x is not equal to 0. Those are the two things for the limit of a quotient to work. You need to be able to, if asked on a test, be able to derive the constant multiple limit as well as the limit of a difference. You will be using these formulas over and over again, so hopefully it won't be very difficult to prove these facts.